So here we see the hierarchies are preserved. Okay. Now what I'm going to do, I'm going to do something called as flatten. Flatten is the command to write out a flat netlist. So now I'm going to do write verilog multiple modules and let's look at this netlist. Okay, again I missed this no ATTR switch. Let me use that. So here you see there are no okay, let me split open that for your reference here. So multiple modules hire.v. So I'm showing you both the netlist here. See here the hierarchies of submodule 1 and submodule 2 are preserved, whereas here we don't see them. It's a single netlist. I don't see all these hierarchies here. These hierarchies are flattened out. And I directly see the instantiation of AND gate and this OR gate. This is an OR gate and this is an AND gate, correct? I directly see the instantiation of this AND gate and OR gate directly under the module called multiple modules. I don't see any more U1 and U2. Okay? This is the distinction between using the flattened switch versus not using the flattened switch. Okay? Okay. I'm going to intentionally exit it because I want to read the design again. So now let's say, for example, given multiple modules, first let me read the libert. Given the multiple modules, let's say I want to synthesize at submodule level. Then what is the way to do it? Okay, anyway, in the previous example, I forgot to show you something else. Let me show that first. My lab log file, I'm sorry. Read verilog multiple modules.v. So I'm going to say synth-top multiple modules. So this we have already seen, so I'm going to do the ABC -liberty then I'm going to do a flatten. I'm going to do a show. I forgot to show you this last time. So now you see, previously we saw when we did the show, we saw U1 and U2, correct? We are not seeing U1 and U2 anymore because I flattened it. I'm seeing an AND gate and this is the inverter feeding the NAND gate. So this is an OR gate. So this is your U1, the output of U1 is feeding U2 with another input coming from C. This is what is your whole netlist. This is what is your multiple module looking like. Okay. So when we flatten, we directly see the structure completely, which we didn't see when we did when we executed show before. We saw U1 and U2. We are not seeing U1 and U2 anymore. We are seeing the underlying components within U1 and U2 completely written out flattened. Okay, I will launch USS again. So this time we will do a submodule level synthesis. And I'll also explain what is the need for doing the submodule level synthesis. I'm sorry. I missed the keyword read liberty -lib. Yes. read verilog dot slash no multiple modules dot v. Now we say synth hyphen top. Now as we look at the design, let me show you once again. As we were looking at the design, this is our design, correct? So if you look at this design here, we have U2, we have U1. We don't want to synthesize multiple module. We want to synthesize this at U1 level or U2 level, say for example. We'll see why we do that subsequently. Now I'm going to say synth hyphen top. I'm going to say sub module 1. So I'm going to do a synthesis at sub module 1 level. Though I have read the RTL at top module level, I'm going to do the synthesis at sub module 2 level or sub module 1 level. So now you see it has inferred only one AND gate. It is not inferring the sub module 2 at all. It is just inferred sub module 1. So now I am going to do show, and let me link the design ABC-liberty. So now you're going to see only the AND gate you're seeing. You're not seeing submodule 2, you're not seeing U1 or anything there, correct? This is very important. So now you have created only the submodule 1. So now why will you do this? Let's try to understand. We control the module which we are synthesizing using the keyword synth-top, but let's see why we do this. So why? Why is it? Let's say for example your design looks something like this. This is your top module and you have multiple instantiation of a same component. Let's say you have a design called say a multiplier and your multiplier is instantiated so many times for whatsoever reason. I'll call this as mult1, mult2, mult3, mult4, mult5, mult6. You have 6 instantiation of multipliers. Now instead of synthesizing the multiplier 6 times, you will like to synthesize it once and you will replicate it 6 times. This saves time, correct? You don't want to synthesize your multiplier 6 times. You synthesize it one time and you replicate that netlist 6 times and stitch it together in the top module. Correct? So module level synthesis is preferred when we have multiple instances of same module. Or this is one reason. Okay, this is not the only reason. Our second reason is we want to do divide and conquer approach. Okay, let's say your design is very massive. So this is used in massive designs. Let's say your design is very massive and let's say when you give this massive design to your tool, the tool is not doing a good job. So what you want to do, instead of giving the entire massive design to the tool, you are giving one portion by one portion to the tool so that it writes out a very optimized and sweet netlist to you, and then you stitch all this netlist together at the top level to get the best possible netlist at the top level. So these are the two reasons why we do a submodule level synthesis, and we control which module you are going to synthesize by using the keyword synth-top. In Josys, the keyword is synth-top module name. This controls what module you are going to synthesize it. Okay, this brings us to the end of this lab. Thank you.